Have you ever looked up at the stars on a clear dark night and, lost in the immensity of it all, wondered just how strange the universe really is? It's a question that has captivated thinkers for centuries. Today we're diving into the mind of Albert Einstein, a true visionary. He was the one who fundamentally turned our understanding of space, time, and gravity upside down, challenging everything we thought we knew. His revolutionary theory of relativity revealed mind-bending concepts, like the idea that time can slow down relative to your motion. He showed us that gravity isn't just a force, but rather the bending of space itself, caused by mass and energy. And perhaps most famously, that matter can be converted into pure energy, and vice versa, as described by the iconic equation E=mc². These aren't just abstract theoretical concepts or science fiction. They're the real, verifiable rules that govern our universe, constantly at play all around us. You don't need to be a genius or have a PhD in physics to grasp these ideas, just a bit of curiosity and an open mind. Einstein's relentless curiosity led him to perform thought experiments, like imagining himself riding on a beam of light, traveling at the ultimate speed. This simple act of imagination was the key to revealing a hidden reality, a new way of understanding the cosmos that no one else could quite see at the time. So let's fire up our imaginations and prepare to bend our minds a little. Our journey starts with a simple yet revolutionary question, one that challenged the very foundations of physics. What if the speed of light is always the same, a constant, no matter how fast you're moving or in what direction? This seemingly simple idea is the key to unlocking the secrets of special relativity, the first step in understanding Einstein's genius. It's an idea that has profound consequences, forcing us to fundamentally rethink our understanding of space and time and their relationship to each other. We must begin to see them not as separate entities, but as a single, interwoven, flexible fabric, spacetime. And this fabric, this spacetime, can be stretched and squeezed, warped and curved, in the most remarkable and unexpected ways, shaping the very structure of the universe. Imagine standing by a road, perhaps on a warm summer day. You're observing the world around you, taking in the sights and sounds of everyday life. Suddenly, a car speeds by, a blur of motion and sound. It's moving much faster than you are, a stark contrast in relative speeds. If you're in another car, moving at a different pace, the difference in speed between you and the other vehicle is just simple math. You can easily calculate how much faster or slower they're going relative to you. But light, the fundamental constant of the universe, doesn't play by those intuitive rules. Einstein, in his groundbreaking work, realized the speed of light in a vacuum is always the same, a universal constant. It remains constant, approximately 299,792,458 meters per second, no matter how fast you're moving relative to the light source. This is a cornerstone of special relativity. This seemingly bizarre concept has been rigorously tested and proven by countless experiments over the years, solidifying its place in modern physics. Because the speed of light never changes, regardless of the observer's motion, space, and time themselves, the very fabric of our reality must stretch or shrink, expand or contract to keep the speed of light constant for all observers, maintaining the universe's fundamental laws. That means your measurement of distance and time, the very way you perceive the world, can differ, sometimes subtly, sometimes dramatically, from someone else's, if you're moving at significantly different speeds relative to each other. We don't typically notice this in our daily lives because we move at speeds far below the speed of light. But for the universe at large, and for objects moving at relativistic speeds, it's a fundamental aspect of reality. Special relativity specifically deals with objects moving at constant speeds in a straight line, not accelerating, not changing direction. It's a simplified model, but a powerful one. It shows us in a profound way that space and time are not absolute and fixed, but are dynamic, inextricably linked, forming a four-dimensional continuum that we call spacetime, a concept that revolutionized our understanding of the universe. The faster you move through space, approaching the speed of light, the slower you move through time, relative to a stationary observer. This is time dilation. It's a cosmic trade-off, a fundamental balancing act, built directly into the very fabric of existence, shaping the universe as we know it. That's how the universe elegantly keeps its ultimate speed limit, the speed of light, intact, ensuring the consistency of physical laws throughout the cosmos. Let's dive into time dilation, one of the most mind-bending concepts in physics. It challenges our everyday understanding of time as something constant and universal. Time dilation describes a phenomenon where time itself passes at different rates for different people, depending on their relative motion or the gravitational field they're in. It's not just a theoretical idea, it's a real effect that has been experimentally verified. To understand this, imagine a spaceship traveling through space with a special clock inside. This clock works by bouncing light between two mirrors. Each bounce represents a tick of the clock. For the astronaut inside the spaceship, the light travels a short, straight path up and down between the mirrors. The ticks are regular and consistent. But now, imagine observing this spaceship from Earth. Because the ship is moving, the light beam appears to travel a longer diagonal path as it bounces between the mirrors. Here's the crucial part. The speed of light is a universal constant. It's the same for all observers, regardless of their motion. Since the speed of light can't change, and the light has to travel a longer distance from our perspective on Earth, the clock on the ship must tick slower to compensate. This isn't just an illusion. Time genuinely passes more slowly for the astronaut relative to us on Earth. The faster the spaceship travels, the more pronounced this effect becomes. At near light speed, a decade for you could be a century or even longer for those on Earth. The difference in experienced time grows exponentially as you approach the speed of light. This isn't just theory or a thought experiment. Time dilation has been directly measured. For example, atomic clocks on airplanes, which travel at relatively high speeds, run a tiny bit slower than those on the ground. And the amount of time difference is exactly as Einstein predicted with his theory of relativity. Time is relative, and we've measured it with incredible precision. The faster you go, the more pronounced the effect of time dilation becomes. So imagine the possibilities. If you could travel at 99.5% the speed of light, you'd experience time slowing down so dramatically that you'd age just 10 years while 100 years pass on Earth, transforming the world in ways you can scarcely imagine. When you returned, you'd be stepping into a completely different future world. This is the real, measurable power of relativity, a fundamental aspect of how the universe works. Time travel, at least to the future, isn't just science fiction. It's built into the very fabric of the universe, a consequence of the mind-boggling reality of time dilation. E equals mc squared, the most famous equation in science. It tells us mass and energy are two sides of the same coin. Even a tiny bit of mass can become a huge amount of energy, thanks to the speed of light squared. That's why nuclear power and atomic bombs are possible. A small amount of mass turns into tremendous energy. The sun converts millions of tons of mass into light and heat every second, powering life on Earth. But this equation applies everywhere. Even lifting a book or charging a battery changes its mass by a minuscule amount. E equals mc2 reveals a deep unity. Everything is, at its core, frozen energy. It's not just about explosions or stars. It's about the fundamental nature of reality. Mass is concentrated energy, and energy can become mass. This insight changed physics forever. Einstein's equation connects the everyday to the cosmic. The universe is made of energy in disguise. After special relativity, Einstein tackled gravity itself. Newton saw gravity as a mysterious force, but Einstein saw something deeper. He realized gravity is the curvature of spacetime. Picture a stretched rubber sheet. A heavy ball creates a dent, and smaller objects roll toward it. Not because of a force, but because of the curve. The sun warps spacetime, and planets follow curved paths, what we call orbits. The Earth isn't pulled down, it moves along the curve in spacetime. This applies everywhere. Matter tells spacetime how to curve, and curved spacetime tells matter how to move. Gravity is geometry, not a force. Orbits, falling objects, even light, all follow the curves of spacetime. Einstein's vision replaced Newton's invisible force with a beautiful, flexible fabric. The universe is shaped by mass and energy. This is general relativity. General relativity predicted something wild: gravity should bend light. Newton's laws said gravity only affects mass, but Einstein said even massless light follows spacetime's curves. In 1919, during a solar eclipse, astronomers photographed stars near the sun. The starlight was bent, shifting their positions, just as Einstein predicted. The results made headlines worldwide. Einstein became a celebrity overnight. It was a triumph for science, a bold theory confirmed by observation. Light itself bowed to the curvature of spacetime. The universe had revealed one of its deepest secrets. Relativity isn't just cosmic theory, it's in your pocket. GPS satellites orbit Earth with atomic clocks, moving fast and far from gravity's pull. Special relativity makes their clocks tick slower. General relativity makes them tick faster. The net effect satellite clocks run about 38 microseconds faster per day than clocks on Earth. If uncorrected, GPS would be off by miles within a day. Engineers use Einstein's equations to keep your maps accurate. Without relativity, GPS wouldn't work. Every time you navigate, you're using Einstein's ideas. The universe's weirdness is part of your daily life. Relativity keeps you on track, literally. Let's try the famous twin paradox. One twin, Stella, rockets to a star at 99% the speed of light. Her sister Terra stays on Earth. For Terra, the trip takes 20 years. For Stella, just 3 years pass. When Stella returns, she's much younger than her twin. Time slowed for Stella, but not for Terra. Space itself also contracts for Stella. Her journey seems shorter. This is how the universe keeps the speed of light constant. But can we ever reach light speed? No, mass increases as you go faster, needing infinite energy to reach light speed. Only light itself can travel that fast. The twin paradox shows time and space are flexible, not fixed. Relativity sets a cosmic speed limit we can never cross. We've toured Einstein's universe, the speed of light, time dilation, mc2, and the curvature of spacetime. These ideas challenge our intuition and reveal a universe stranger than we ever imagined. Time and space are dynamic, woven together and shaped by mass and energy. Einstein gave us new eyes to see the cosmos. Which part amazed you most? Traveling into the future, gravity bending light, or the unity of mass and energy? Hold on to that wonder. Curiosity drives discovery. Keep asking questions and looking up. Relativity describes the grand scale, but the quantum world is even weirder. That's the next great adventure in understanding the universe. The